Lesson 4: Amplitude Modulation. Modulation is the process of altering a characteristic of the carrier in accordance with the instantaneous value of the intelligence signal. The characteristics of the carrier that can be varied are amplitude, frequency, and phase. Demodulation is the process of recovering the intelligence signal from a modulated carrier signal. This is an example of a carrier signal which is considered as a sine wave carrier. Mathematically, instantaneous carrier amplitude is equals to peak carrier amplitude sine carrier region's frequency multiplied by t plus carrier phase. Reasons for modulation. Modulation allows us to send a signal over a bandpass frequency range. If every signal gets its own frequency range, then we can transmit multiple signals simultaneously over a single channel, all using different frequency ranges. Another reason to modulate a signal is to allow the use of a smaller antenna. A baseband low-frequency signal would need a Hodge antenna because in order to be efficient, the antenna needs to be about 1/10 of the length of the wavelength. Modulation shifts the baseband signal up to a much higher frequency which has a smaller wavelength and allow the use of a much smaller antenna.
FCC emission designations. Emission designations. An emission designator is a code associated with a frequency that gives information about the frequency's bandwidth and the nature of the signal on the frequency. Emissions are designated according to their classification and necessary bandwidth. A minimum of 3 symbols are used to describe the basic characteristic of a radio waves. Emissions are classified and symbolized according to the following characteristics. First symbol means type of modulation of the main carrier. Second symbol, nature of signals modulating the main carrier. Third symbol is a type of information to be transmitted. First symbol, emission of unmodulated carrier means N. Emission in which the main carrier is amplitude modulated, including cases where subcarriers are angle modulated. A means double-sided band. H, single-sided band, full carrier. R, single-sided band, reduced or variable level carrier. J, single-sided band, suppressed carrier. V, independent sideband. C, vestigial sideband. Emission in which the main carrier is an angle modulated. F means frequency modulation. G, phase modulation. Emission in which the main carrier is amplitude and angle modulated either simultaneously or in a pre-established sequence means D. Emission of pulses. Sequence of unmodulated pulses means P. A sequence of pulses. K means modulated in amplitude. L modulated in width or duration. M means modulated in position or phase. Q, in which the carrier is angle modulated during the period of the pulse. V, which is a combination of the foregoing or is produced by other means. Cases not covered above, in which an emission consists of the main carrier modulated either simultaneously or in pre-established sequence. A combination of two or more of the following modes, amplitude, angle, and pulse, means W. X means cases not otherwise covered. Second symbol. 0 means no modulating signal. 1 means a single channel containing quantized or digital information without the use of modulating subcarrier, excluding time division multiplex. 2. A single channel containing quantized or digital information with the use of modulating subcarrier, excluding time division multiplex. 3. A single channel containing analog information. 7. Two or more channels containing quantized or digital information. 8. Two or more channels containing analog information. 9. Composite system with one or more channels containing quantized or digital information together with one or more channels containing analog information. Third symbol. N means no information transmitted. A. Telegraphy for oral reception. B. Telegraphy for automatic reception. C. Fast mile. D. Data transmission, telemetry, and telecommand. E. Telephony including sound broadcasting. F. Television or video. W. Combination of the above. If you have ever obtained a license from the PCC or spent time looking at your radio's manual, you will notice a 7-digit code like 20K0F3E. It's not there for decoration. It actually means something. The first four digits in the example above stand for occupied bandwidth in kilohertz. So, 20K0 would signify 20 kilohertz of bandwidth. The last three digits signify the type of emission. F3E stands for analog voice.
Amplitude modulation. Amplitude modulation is the simplest way of superimposing the characteristic of the intelligence signal onto a carrier. The AM signal is produced by varying the amplitude of the carrier signal in proportion to the instantaneous amplitude of the intelligence signal. Amplitude modulation is a process where the maximum amplitude of the carrier wave is made proportional to the instantaneous value of the modulating signal. In amplitude modulation, we are going to change the amplitude according to the signal waves, and only the amplitude of the carrier wave is changed. These are the waveforms of the amplitude modulation. The modulating signal shows the audio-electrical signal of frequency. The modulating signal, which has constant frequency, will add the sound wave representing the actual audio to the base signal or the carrier signal, resulting in the amplitude of the wave changing accordingly. The carrier signal shows the carrier wave of an amplitude which varied linearly with respect to the modulating signal. The resulting AM, or the AM signal, is to be noted that the amplitudes of both positive and negative half cycles of carrier wave are changed in accordance with the signal. Thus, the amplitude of the modulated wave possesses the frequency of the audio signal wave. The trace of the peaks in the AM wave is called the envelope, which has the same shape as the modulating signal. Let us consider the equation of this modulating signal be the instantaneous value of modulating signal equal to E sub m, where E sub m is the peak amplitude of the modulating signal. So, E sub m sine omega mt, where omega m indicates the angular modulating frequency, which is equal to 2 pi fm, where fm is the frequency of the modulating signal. Similarly, for the carrier signal, again, we are to take the instantaneous value of the carrier signal, which is represented as a small e sub c, which is equal to the amplitude of the carrier signal, sine omega c t. And again, the omega c can be written as 2 pi fc, where fc is the frequency of the carrier. And for AM, we can write the instantaneous value of AM equal to the amplitude of AM sine of omega ct. Deriving the amplitude would be equal to E sub c plus the instantaneous value of the modulating signal times t. Therefore, the equation of the AM will become the instantaneous value of AM is equal to E sub c plus the instantaneous value of the modulating signal times sine omega ct. Substituting the instantaneous value of the modulating signal, the AM equation will become instantaneous value of AM is equal to E sub c plus E sub m sine omega mt times sine omega ct. E sub c sine omega ct plus E sub m sine omega mt times sine omega ct.
Modulation index. The relationship between the peak voltage of the modulating signal Vm and the peak voltage of the unmodulated carrier Bc is modulation index equals to modulating signal Vm over unmodulated carrier Vc. Modulation index. In this slide, we see how the graph represents the Vmax and Vmin. In Vmax, the equation is Vmax equals to peak voltage of the carrier signal plus peak voltage of the intelligent signal. And the Vmin is peak voltage of the carrier signal minus peak voltage of the intelligent signal. Thus, the modulation index can be expressed as Em over Ec or equals to Vmax minus Vmin over Vmax plus Vmin. The term that describes the amount of amplitude change in an AM waveform is called the index of modulation, and it is also called coefficient of modulation, modulation factor, or modulation depth. Percentage of modulation is equals to modulation index times 100. The classification according to degree or modulation. In the first graph or figure that we see is in the under modulation. It is M less than 1 and EM less than EC. Under modulation occurs when the maximum amplitude of the message signal or modulating signal is less than the maximum amplitude of the carrier signal. And the second picture is the overmodulation, where M is greater than 1 and EM is greater than EC. Overmodulation occurs when the maximum amplitude of the message signal or modulating signal is greater than the maximum amplitude of the carrier signal. And last is the perfect modulation, where M equals to 1 and EM equals to EC. Perfect modulation occurs when the maximum amplitude of the message signal or modulating signal is exactly equal to the maximum amplitude of the carrier signal.
When a single frequency sine wave amplitude modulates a carrier, the modulating process causes two side frequencies to be generated above and below the carrier frequency by an amount equal to the modulating frequency, f sub m. The upper side frequency, which is f sub u sf, and the lower side frequency, which is the f sub l sf, can be determined from f sub u SF is equal to F sub C plus F sub M, and F sub L SF is equal to F sub C minus F sub M. Complex modulating signal, such as a square wave, consists of a fundamental sine wave frequency and many harmonics, causing many side frequency to be generated. The highest upper side frequency and the lowest lower side frequency are determined by the highest harmonic frequency, while the highest lower side frequency and the lowest upper side frequency are determined by the lowest harmonic frequency. The band of frequencies between quantity f sub c plus f sub m mean and quantity f sub c plus f sub m max is called the upper sideband, while the band of frequencies between quantity f sub c minus f sub m mean and quantity f sub c minus f sub m max is called the lower sideband. The difference between the highest upper side frequency and lowest lower side frequency is the bandwidth occupied by the modulated carrier. Therefore, the bandwidth can be calculated from bandwidth is equal to the quantity of f sub c plus f sub m max minus the quantity f sub c minus f sub m max, which is equal to 2 times f sub m max. This bandwidth occupied by the modulated carrier is the reason a modulated carrier is referred to as broadband transmission. Higher modulating frequencies means the wider the modulated carrier bandwidth. When a carrier is overmodulated, the resulting distorted wave shape generates harmonics that generate additional side frequencies. This causes the transmitted bandwidth to increase and interfere with other signals. This harmonic generated sideband interference is called splatter. When an AM signal is observed on an oscilloscope, it is observed in the time domain, which is voltage as a function time. The time domain display gives no indication of sidebands. In order to observe the sidebands generated by a modulated carrier, the frequency spectrum of the modulated carrier must be displayed in the frequency domain. Sine wave voltage levels as a function of frequency on a spectrum analyzer. Sine wave modulated AM signal. A composite of a carrier and two side frequencies, and each of these signals transmits power. The total power transmitted is the sum of the carrier power and the power in the two side frequencies. Therefore, P sub t is equal to P sub c plus P sub USF plus P sub LSF. Total power transmitted, P sub t, can also be determined from the modulation index M using the equation P sub t is equal to P sub c times the quantity 1 plus m squared over 2 is equal to P sub c plus P sub c times the quantity m squared over 2, which is equal to P sub c plus P sub c times the quantity m squared over 4 plus P sub c times the quantity m squared minus 4. Therefore, the total power in the side frequencies P sub SF is equal to P sub c times the quantity m squared over 2, and the power in each side frequency is equal to P sub c times the quantity m squared over 4.